Next is Huffman elimination. Okay. Also known as Huffman, of course, involves Huffman exhaustive methylation. Let us see this part first. The exhaustive methylation part, taking a primary amine into consideration. Okay. This is a primary amine. In fact, it has to be NH2, but for convenience sake, I've taken it as NH minus NH plus, so that I can show you the way the reaction proceeds. Okay. Now, see this NH minus attacks this carbon from the backside. Whenever I say backside, I hope you can recall that it is SN2 mechanism. So here, the thing that gets eliminated is HI. You got H plus, and this iodine is going off with the bonded pair. Okay. Now, what do we get? Come on. First methylation is done. You got a methyl group. Okay. So this is secondary amine. Now let me just make a small change in this. Again, for the next step, I've made some arrangements. N minus and H plus is what I need because I'm going to go for SN2 again, right? So SN2, then of course the thing that is eliminated is HI. So here you get a tertiary amine, right? N, then CH3, another CH. We got two methyl groups connected. And also a lone pair is available at nitrogen. Now again, when you treat it with methyl iodide, see there is nothing to eliminate, right? Now when there is nothing to eliminate, simple thing is the lone pair on nitrogen comes into picture. You have no H plus to remove, so simply it gets connected this way. Look at this. See, N, first methyl, second methyl, then third methyl. See, because nitrogen has got just four electrons around it, it gets a positive charge because it has one electron less than what it has to have. So this is now a quaternary ammonium salt. Okay. It's just like your ammonium chloride, NH4 plus. Three hydrogens are replaced by these methyl groups and a hydrogen is replaced by this group. I have not taken the negative part, I minus, but still it is the ammonium salt. Now, when this ammonium salt is treated with moist silver oxide, see, up to the formation of quaternary ammonium salt, we call it exhaustive methylation. Now, when treated with moist silver oxide, see, when I say moist, I'll have water with me, water with silver oxide. When these two react, you get silver hydroxide. Okay. Now, the point is Now this OH minus, of course, comes into picture, but let me show you when. Take the same thing again. Consider a hydrogen this way. Now using, say, OH minus of the silver hydroxide, let us do this. Take out the H plus, I mean without the bonded pair, this comes here, and then this goes here. That's it. This is what happens. Okay, so in this case, of course, on heating, a kind of E2 elimination occurs, and you'll get first a bond here, then of course the tertiary amine thing, CH3 taken thrice N. This is what you get. So you got your alkene, and even here also, let us take the mechanism. Right up to this step, it is methylation, exhaustive methylation. You have treated a primary amine with 3 molecules of methyl iodide. Then it's with silver oxide moist. Then on heating, it undergoes, of course, E2 elimination. Now the mechanism. Again, the mechanism is of syn type. I mean, stereochemistry is syn, regiochemistry is Hoffman. Elimination is of syn type, and the product formation is via Hoffman type. So come on. Let me take a hydrogen out for convenience. Then this is a quaternary ammonium salt we have. Take OH minus, abstracts the H plus. Immediately this goes. Okay. That's it. Let me show you the transition state. CH3, CH. Now this bond is going to get broken, and a new bond is going to get formed. This one. Okay, so this is the bond that is going to get broken. This is the bond that is going to get formed. You already got a bond here, a fresh bond. This is of course BF, then CH2. Now this bond is going to get broken. NMe3 plus. That's it. I think that is okay. Now, this is the transition. Now, this gives rise to, I mean, it simply decomposes quickly because transition state is a short-lived one. So, finally, we get CH3, then CH, double bond CH, right? And from this end, we get NMe3, right? Then from this area, we get water molecule. Okay, that's it. So that is all about the elimination. Okay, these are all very important. We have seen the pyrolysis of esters, the pyrolysis of xanthates, Cope elimination, and this is Huffman elimination now. Okay. Now the preparation methods. In fact, the previous ones what we have discussed are also the preparations. We have prepared the alkenes by elimination only. Now let us see the other preparation methods like say hydrogenation. Now consider an alkyne. Alkyne with I have some very interesting reagents with hydrogen. In fact, hydrogenation itself refers to addition of hydrogen. With hydrogen, in the presence of palladium barium sulfate in quinoline and sulfur. A very interesting reagent. This one is the reagent. Say this is of course called Lindlar's catalyst. Very important. Now in this catalyst we have certain interesting points. No doubt palladium is a catalyst. Barium sulfate is a catalytic poison. Why is this catalytic poison used? You know, a poison actually reduces the activity of the catalyst. Supposing if you go for hydrogenation in the presence of Lindlar's catalyst, you get this. Okay. This is what you get if you use Lindlar's catalyst. But if you don't use this, reaction doesn't stop. Now the reaction doesn't stop and it actually continues till you get alkane. Here you got your alkene because you have used a poison, barium sulfate. Otherwise, the catalyst simply allows the next step, which of course gives alkane. So to stop the reaction at this stage, I mean for partial hydrogenation, we use Lindlar's catalyst. And there is something like quinoline sulfur. What is the use of this? Yes, quinoline sulfur is of course used to increase rate of poisoning of the catalyst. Very interesting. So you got catalyst, catalytic poison, and something which increases the rate of poisoning of the catalyst. Okay. So this is the use of Lindlar's catalyst. And let me also tell you that here with the Lindlar's catalyst, we will have syn addition. You know what syn addition is? Addition of the two hydrogens across the multiple bond from the same side. So that is the use of Lindlar's reagent, Lindlar's catalyst. Now seriously concentrate on the reagents and their uses. The organic chemistry, after all, deals with the reactions and the reagents. Now let me go for another reagent. Same hydrogen, addition of hydrogen using a catalyst nickel boride. Nickel boride is of course called P2 catalyst. I can tell you that this is phase 2 catalyst. Okay, so even here also we get the same product. And then we have used this earlier also. Diamide. Even here also it is the syn addition. Okay. In all these cases, it is a syn addition. I've given the mechanism with the diamide from alkenes to alkanes. I mean, in the preparation of alkanes from alkenes. So these are all the reactions in which alkyne is converted into alkene. So I can tell you that this is all partial hydrogenation. So we can write this way. Okay, right. Now it is hydroboration and acidolysis. Discussed even in the preparations of alkanes. Come on. So in this case, we go for BH3 tetrahydrofuran, THF, followed by acidolysis using acetic acid. Even this also is a syn addition. Okay, we get R, CH, double bond, CHR. But actually in this there is a problem. The problem with this reagent is, see, the reaction does not stop at alkenes stage. May even get reduced to alkanes. So to prevent this, yes, because we are actually planning to prepare alkenes. We don't want alkanes now. So in order to stop the reaction at alkene stage, you cannot go for the basic BH3THF ACOH reagent, because there is every possibility of the alkene getting reduced to alkene. So to prevent this, we use an interesting reagent. a reagent dicyamyl borane is used. Okay, what do you mean by dicyamyl borane? Let me tell you. See, this can of course be written as it is, di. See, the S refers to secondary. Then this I refers to iso. And this amyl. Amyl is nothing but pentyl. Amyl is nothing but pentyl. Of course, borane. So disecondary isoamyl or isopentyl borane. Let me give you the structure. Come on. Say this is iso. See, borane is actually BH3, right? Now you still have a hydrogen connected to boron. That means two hydrogens have been replaced by this particular group. Now let me show you what all are these. See, this is of course iso. You got di, and see, the thing that has point of connectivity is a secondary thing, secondary carbon. So come on, di, secondary, iso, and the overall thing is amyl or pentyl. Then the final thing is borane. Di, secondary, iso, amyl or pentyl borane. This is what we use for partial reduction of the alkynes. I mean to get alkenes, which do not further get reduced to alkanes. No further reaction with the dicyamyl borane. I'll show you why, taking the mechanism. Okay. Now, interesting mechanism. Of course, here the stereochemistry is in from the same side. Now, in the first step, let us go for hydroboration. Alkyne. So this is our dicyamyl borane. Dicyamyl borane. In the first step, as usual, you can connect this here, and this gets connected to this. The same thing what we have seen with hydroboration in the preparation of alkenes. Very interesting. Now, R, C, we have already got a triple bond. Now this is going to get broken, then this, it's okay. Now a fresh bond is going to get formed between carbon and hydrogen. This bond, of course, gets broken, right? Then, of course, two Cr groups. In this one, a new bond, right? So this is again a kind of transition state. Okay. Then now it decomposes to form R, C. You got a hydrogen, double bond, C, R, and here we got a boron with two Cr groups. I mean secondary isoamyl groups. But here the thing to be concentrated is where from this hydrogen is obtained. So this is from the dicyamyl borane, SiA2BH. That's it. Now the second step. Now this with the acetic acid. See, we don't have any hydrogen to go for the first step in a repetitive manner. No, you don't have. You don't have hydrogen. If suppose you consider BH3, then you will have two more steps to go for. But here you are limiting the steps to just one. Right. Come on. Then with acetic acid. Okay. Boron is a Lewis acid, and you are giving it a pair of electron. You know what AC is? It is acetyl. So now you get RCH double bond CR, right? You got boron, SiA, SiA, then of course O, which is connected, then H, then the acetyl group. But oxygen, of course, will still have a pair of electron. So let me put a positive charge because it will have 5 electrons around it. Then it is this. As and when the bond is formed with hydrogen, this goes off and you'll get the final product. Come on, check this out. R, C, H, double bond, C, R. You got another hydrogen, but interestingly, this is not from your dicyamyl borane. This is from acetic acid. And now the byproduct is you got ACO connected to boron, which has already got two Cr groups. Okay, so this is how we can show syn addition. And see, knowing the mechanism is very important because when hydrogen is replaced by deuterium, then we get confused of what is to be added to which triple bonded carbon. I'll give you that.